Hello, viewers. In today's session, we are going to discuss two very important problems from differential equations, right? So here we'll discuss two important differential equations and we'll find out the solution of these differential equations by the method of variable separable form, right? So let us take these equations one by one. So here first we have this equation in which we have the logarithm of y prime. So y prime is the derivative of y with respect to x, and log of y prime is equal to 2x plus y, and the initial conditions are y of 0 is equal to 0, right? So we'll solve this differential equation by method of variable separable form. So now let us write this equation as the log of dy over dx, and this is equal to 2x plus y, right? So here to convert this differential equation into variable separable form, what we will do, will first get rid of this log, right? That is the natural log of dy over dx. So here we'll take the exponent of both sides, and here we'll take e raised to log of dy over dx, right? So raising both sides to the power of e, we have e raised to log of dy over dx, and here we have e raised to 2x plus y, right? So here I will make use of this result, that is e raised to log of a is equal to a. So here we have dy over dx is equal to e raised to 2x times e raised to y, right? So here we can use the result, that is e raised to a plus b is equal to e raised to a times e raised to b, right? So now we can separate the variables here, and taking all the y's to the one side and all the x to the other side, we have dy over e raised to y is equal to e raised to 2x dx. And now we can write e raised to minus y dy is equal to e raised to 2x dx, right? Now integrating both sides, so we have e raised to minus y dy, and here we have e raised to 2x dx, and c is the constant of integration, right? And we'll find this constant of integration by using this condition. So the integral of e raised to minus y is minus e raised to minus y, and here we have e raised to 2x over 2 plus c, right? So this is the general solution of this differential equation containing this constant of integration, right? So to find out the value of this constant of integration, let us use this condition. So we have y of 0 is equal to 0. It implies that when x is 0, y is equal to 0. So substituting these values over here, we have minus e raised to minus 0, then we have e raised to 2 times 0 over 2 plus c. So this is e raised to 0, e raised to 0 is 1, so we have minus 1. Here again we have e raised to 0, which is 1, so we have half plus c. So c is equal to minus 1 minus half, that is minus 3 by 2, right? So resubstituting this value in this equation, we have minus e raised to minus y, e raised to 2x over 2, and then we have minus 3 by 2. So now rearranging the terms, so multiplying both sides by 2, we can now have minus 2 e raised to minus y, and here we have e raised to 2x minus 3. So taking minus 2 times e raised to minus y to the right hand side, we have e raised to 2x plus 2 times e raised to minus y minus 3 is equal to 0, right? So this is the particular solution of this differential equation when the conditions are x is equal to 0 and y is equal to 0, and this is the general solution of this differential equation. Now let us consider this differential equation. So here we have to find out the general solution of this differential equation containing the second derivative of y with respect to x. So we have log y double prime is equal to x, right? Again, what we will do, we'll get rid of this log term. So we'll raise both the sides to the power of e. So we have e raised to log of y double prime, and here we have e raised to x, right? And again, using this important result, that is e raised to log of a is equal to a. So here the value of a is y double prime, so we have y double prime is equal to e raised to x. So now we can write this differential equation as d2y over dx2 is equal to e raised to x. So now what we will do to get the value of this y as a function of x, will integrate both sides with respect to x. So we can rewrite this equation as d by dx of dy over dx. So this is the notation for the second derivative, and here we have e raised to x. Now integrating both sides with respect to x, we can now write this expression, that is d by dx of dy over dx, and here we have dx, and here we have e raised to x and dx, right? So the integral of dy over dx with respect to x is simply dy over dx, and here we have e raised to x with c1 as the constant of integration, right? So again, we have reduced this differential equation into this equation, and it contains the first derivative of y with respect to x. So let us again integrate both sides, right? So separating the variables, what we will do, we'll write dy is equal to e raised to x plus c1, and here we have dx. Now integrating both sides, we have e raised to x plus c1, and here we have dx. So here we have simply y, and here the integral, that is e raised to x dx, then we have integral c1 dx, and then we'll add a second constant of integration, that is c2. So we can now write y is equal to e raised to x, and here we have c1x, because the integral dx is simply x, and here we have c2, right? So this is the general solution of this differential equation. We can also write it as y of x is equal to e raised to x plus c1x plus c2, right? And we can easily see that the general solution contains two arbitrary constants, right? And from here we can see that the order of the differential equation is 2 and the degree is 1, right? So the order is 2, so the solution the general solution must contain two arbitrary constants, right? So this is the general solution of this differential equation. So now let us consider one more problem related to variable separable form. So here we have to solve this differential equation. Dy over dx is equal to y times sine of 2x, and the conditions are y of 0 is equal to 1, right? So here what we will do, we'll separate the variables. So we'll take all the y's to one side and all the x to the other side. So we can now write dy over y, and then we have sine 2x, and here we have dx. So now integrating both sides, so we have integral dy over y, and here we have integral sine 2x dx. So now the integral 1 over y dy is simply a log of y. And here the integral sine 2x is minus 1 over 2 cos of 2x, and c is the constant of integration. So here we have used this result, that is integral dx over x is log of x, and the integral sine ax dx is equal to minus 1 over a cos of ax, right? So now we have this expression, and with the help of this initial condition, we have to find the value of this constant of integration. So we have y of 0 is equal to 1. It implies that when x is 0, we have y is equal to 1. So let us substitute x is equal to 0 over here, and y is equal to 1 over here. So we have log of 1 is equal to minus half. Then we have cos of 2 times 0 plus c. So log of 1 is 0, and here we have 0. Then we can write minus half cos of 0 plus c, and cosine 0 is equal to 1. So we have 0 is equal to minus half times 1 plus c. So c is equal to half, right? So now substituting c is equal to half over here, we have log of y is equal to minus half cos of 2x plus half, right? So now multiplying throughout by 2, we can now write 2 times log of y is equal to minus cos 2x plus 1, right? Because 2 and 2 get cancelled, and here we have 2 times log of y. So we can also write it as 2 log y is equal to 1 minus cosine 2x. So now here we'll make use of some trigonometry. We know that cos of 2 theta is equal to 1 minus 2 sine square theta, right? So this is an important double angle formula for cosine function, and we can also rewrite this expression as 2 sine square theta is equal to 1 minus cos of 2 theta, right? So here we have 1 minus cos 2x. So now we can write 2 log y is equal to 2 sine square x, right? So using this result, 1 minus cos 2 theta, and here we have 1 minus cos 2x. So we can write 2 sine square x. Now this 2 and this 2 get cancelled, so we are left with log of y is equal to sine square x. So now raising both sides to the power of e, we have e raised to log of y is equal to e raised to sine square x, right? And here again we'll make use of this result, e raised to log of a is equal to a. So here we have e raised to log y, so we can simply write it as y, and y is equal to e raised to sine square x, right? So this is the particular solution of this differential equation provided y of 0 is equal to 1, right? And this expression that is log of y is equal to minus half cos 2x plus c, it gives us the general solution of this differential equation.